Okay, now I hit F11. Haha. Okay.
Great. So the next talk is Owen Lynch, who's going to tell us about semagrams and nested wiring diagrams. Thanks, Owen.
Okay, so this is a software demo, but we're going to start with a math problem. So let top be a good category of spaces. You probably all have opinions about which the best, what exact definition you should use for top, but that's not really important to this. But it has to be good. So then fix a small category C. We call functors from C to set, C sets. Let shape be any functor from C op to top. Then ship star, let this be the left con extension of ship along the uneta embedding, which is, of course, computed by the coend. What the hell am I talking about? So let me give you an example. So consider the following category. Okay, we can turn this off.
Can you also hide meaning controls or something?
Is there?
Hide meaning controls.
Oh, there we go. Excellent. Okay. So let C be this category. We like this category a lot in Catlab. This is the schema for graphs. So it has two objects and four morphisms, identity morphisms not pictured. So set to the C is the category of graphs. A graph is a set of edges, a set of vertices, and then two functions between them, which give the source and target of each vertex. Now, if we defined shape from C op to your favorite category of topological spaces by sending E to the interval and V to the point, and then we send source to the inclusion of the point into the left-hand side of the interval, and target to the inclusion of the point into the right hand of the interval. Then shape star, which is shape star. This left con extension takes the combinatorial representation of a graph, which is a C set, to the intuitive topological space that we think of when we draw a graph. So, yeah, what's up?
The covering, really?
What do you mean? The covering?
Which is the intuitive topology?
Do we have, yeah. It's like, let X be the space of pixels, or space of, pixels that are colored black. That's the topological space up to homotopy. But does that make sense? It's like an actual, this is, homotopy equivalent to S1. It's actually just topological space. It's just circle, yeah. But yeah, if you do this to the combinatorial representation of the Peterson graph, you get the Peterson graph as a topological space. So now, what if all you needed to do to create a graphical editor was to specify ship? All you needed to do was say, okay, for each object in my schema, for each object in my category C, I tell you what shape it should be, and then I tell you how the shapes interconnect. That was the original dream of Semagrams 2.5 years ago, but it's not that easy. But it was a cool idea. Why is it not that easy? Well, geometry is not topology. So I mean, from the perspective of topology, this and this these are the same, but many people would be unhappy with me if this was how my graphical editor displayed graphs. Or like even worse, like scale is also important. Another thing that's hard, well, mutation is hard. You know, this is something, if you've ever programmed before, this is like the big controversy of programming in the last 50 years. Like, how do we do mutation right? And then layered on top of mutation, interactivity. So how do you express like actions? I want to be able to like click on this and drag it around. Give me a category for that. No, I don't know what the category for that is. But then another thing is like, okay, domain-specific UI. So when you're doing these graphical editors, sure, okay, the topological version of, or like these like nice pictures are maybe mathematically elegant, but if you're working on, as you will see, an editor for Petri nets, then you might want things that are like specific to biology. So how do you like work that in? Overlap is the bane of my existence. When you have, you know, these I just drew as points, but actually you want them as like circles. Now what happens if you like drag the circle? Which one goes on top? It's terrible. Communication with algebraic Julia. So ultimately this is supposed to be a front end to, you know, actual computation. So yeah, I work on algebraic Julia. It's a big Julia project for doing applied category theory. You want to be able to use this to edit stuff that can actually be computed on. How do you do that communication? Text is awful. Resizing boxes around text. There's a million little details, like when you draw arrows, that looks terrible. That looks good, the little gap. Style in general, like choosing pretty colors. And then finally, the big one is nobody wants to have your, you have your UI. Nobody wants to draw like a 50-box wiring diagram. That's a nightmare. In order to like actually make this practical for people to use, you have to be able to like chunk your UI or chunk your stuff so that you have like boxes, and then inside these boxes you have boxes, and you have to not show everything on the screen at once so you don't overwhelm people. And the recursive nested structure, well, that's in the name of the talk, because that's what I've been working on recently and thinking about a lot. I don't have a full solution, but I'm going to talk a little bit about also the math of what even does it mean to have this recursive nested structure for wiring diagrams. Okay, so let me give you a little history of what. So I've just talked about a lot of all these design problems. Like we started out with this beautiful idea. What if we can just do left con extensions to make shapes? And then we've sort of, reality has beaten all sorts of nasty things into us. And now I try to actually write it. And so the first step was the Semagrams legacy, which I presented 2 years ago at ACT 2021. And this was a TypeScript application, which means that the configuration to change it from like wiring diagrams to Petri nets to graphs, that was just given by data on the fly. And this was useful because it meant that you didn't have to recompile it to use different, to be in different domains, but it also restricted it a lot. So for instance, I had to like bake in that there were only 3 types of graphical entity: boxes, ports, wires, which is a little restrictive because first of all, like boxes, well, you know, maybe you want circular boxes. How do you lay out the ports around the boxes? Do you have like a box like this where you have ports on the left and right? Or do you have a box like this? I don't know. I never like making people choose from like a list of options. I want to give them an API so you can have whatever custom shapes you want. And then some technical details. I used a virtual DOM library. If you're familiar with React, it's similar. We use mutation, like nasty mutation, non-functional programming, and non-generic adject data structure. And then here's the kicker. This one is maybe a little bit opaque, but whenever there was like a multi-step interaction, we had like, you have to explicitly represent in data the state machine of the interaction. Like user has clicked, user has started to drag, user has ended dragging. And like in general, when you have like more complex interactions, there could be like long state machines that express the behavior. So all of this was not scaling. So I threw it all away. And rewrote in Scala. And so the current version is a Scala.js library. So it's not an application. There are many different applications, well, okay, maybe like two, but that use the library. And the idea there is that instead of having like pre-selected options baked in that you choose via data, you configure it at compile time by using the library in different ways. We have a generic interface for custom shapes. So we've broken out of just box ports and wires. You could have like dinosaurs in your you could have the shape take one of your objects in your schema to the dinosaur space. We use a functional reactive programming library with no virtual DOM. I'm not going to get so into this in this talk, but like this is definitely like a breadcrumb that if you're interested in this space, like look up Laminar. It's a really cool library. We use persistent data structures, which means that instead of mutating the data structure, you make a new one, but then as much as possible, you share data between them so that you don't like copy it every time. And this makes undo and redo is for free because you have every version. And finally, this is sort of the big one. Interactivity is via an asynchronous monad, which removes the necessity of explicit state machines. And I'll get more into exactly how that works in a bit. So the architecture of semagrams is that we have basically four parts. So on up here we have the model, which basically is like the representation of your data, and that model is rendered to the DOM, which, if you're not familiar, it's the document object model. It's the browser. And then the DOM sends events to the application and to the control flow. So the application is sort of like built in, and it keeps track of stuff like, okay, where is the mouse position? What is the user hovering over? Stuff like that. And the control flow is what handles key presses and does like complex multi-part interaction. So I'm going to show how to drag later, and you'll see exactly what that means. So, but before I get too far into the weeds, let's actually see what this looks like. So if I click on this demo, it's a totally blank screen. But I can make it's keyboard driven. I'm a Vim user, so I like, yeah, no like drag and drop. I mean, that maybe I should be less dogmatic, but that's how it is now. And then we can drag these arrows, and you can see, so this is a Petri net, and As I edit this Petri net, the rate equation for the Petri net is updated live here. I can also change the names here. So let's say that this is like infection. Look at how the box resizes when the text moves. That was really hard. And yeah, and we can make this like, I don't know, S. Anyways, this is not the SIR model. But anyway, so this is the Semagrams as a Petri net editor. Can I get out of this? X. There we go. Okay. Oh, wait, where did my... Oh, it's okay. I got to go back. Okay, cool. And this shows off... So the Petri net editor itself mostly uses generic functionality. But then this rate equation live display, that's totally custom. So this shows how, like, because Semagrams is now a library, you can intermix like sort of generic functionality with stuff that's really application specific. And now I'm just going to show off some of the code that like is used in the Petri net editor. So this is the keybindings. We've like generically defined different actions. So for instance, the add at mouse action takes in an object of the schema and says that, and basically, so you see I have the same action for adding a species and adding a transition. The only difference is that this one is species and this one is transition. Here you can see undo, redo. This is like a generic deletion functionality. So sort of setting up custom key bindings for your app is pretty easy. This shows off what I was talking about before, which, yeah, so Spencer wrote this code. This presentation is joint with Spencer, but this code was specifically written by Spencer, and it simplified some much more janky code that I had written. So thanks, Spencer. And this code, so there's this really tricky, yeah, you guys are gonna learn way more about annoying graphic, like GUI design issues than you thought. But when you drag on something, say you click here and you move your mouse a little bit. Now, if you naively implemented dragging, you'd say, okay, I'm just gonna set the center of this blob to my current mouse position. So that would mean you click here, you move it a little bit, and suddenly it moves like this. It doesn't move a little bit. You have to save the offset. So that's what this code does generically. When you start the drag, it saves the offset in this memo, and then it uses that offset to calculate the new position, accounting for where you first clicked, and then it finally finishes something. Also notice here I have unrecord and record. This says you should, while you're dragging, you should not save in the undo stack every single little move. You should only save the overall move.
Manual undo stack management.
Manual, yeah, it's like, there's so much to this. It's like, why couldn't it just be easy like left con extensions? But yeah, okay, so anyways, what I was saying before, with the nesting, so here's a better picture of nesting. We have sort of boxes with boxes inside of them. Now this is like, the way I'm picturing this on the screen, it's all displayed at once. So this is actually not useful in terms of removing overload, but this is just so you can see the structure. And so let's see a demo of this. So this is the famous, David's here. David knows this. This is the lemon meringue pie string diagram. And I'm going to make the lemon meringue, I'm going to do something blasphemous. I'm going to make the lemon meringue pie string diagram better by I just zoomed in to the separate egg box. And so what are the steps in separating an egg? Well, first you have to crack the egg. I learned on YouTube that you can crack eggs just by dropping them. It's kind of cool. All right, kids, don't try this at home. And then we could have like, do the little like egg yolk dance. You know how when you're separating an egg yolk dance. And then, yeah, we can make this. Oops. I wanted to connect this to here. Spencer. There we go. And then, yeah. And now I could label these. This could be like egg, cracked egg. Yeah, etc. Oh. Naked you. Yeah. Oh wait, yeah, wait. This is not how. Do not follow my lemon meringue pie advice. Yeah, okay, there we go. Okay, that's enough of that. So now we go back to the top level. And okay, just to make sure, did that actually save? Yeah, okay, it actually saved. Just kidding. I had no fear about that. I'll actually show you. So let's say I zoom in here. And say I make like an extra output to the egg yolk dance, and now I zoom out. That extra output is there. So it's like it's more complicated. That's actually a great question, because that shows that it's actually more complicated than there's just like wiring diagrams inside wiring diagrams, because the internal ports of this wiring diagram become the external ports of the nested wiring diagram. Yeah. And you see, if we delete that, it also is deleted from here. So it's actually one port.
And it's propagated and delete on the wire.
Oh yeah, that's true.
That's good.
Yeah. Yeah. Thank you for pointing out, because that was a lot of pain to get that to work right, actually. Yeah. Recursive delete of nested parts, nightmare algorithm. Anyways. Yeah.
That's like manually label that inner wire egg, but like
it's true. It should be automatic. Yeah, because, well, really what it should be, I mean, right now, these are just wire labels. They really should be wire and port types. And then there should be like the wire type and the port type have to match up. That's not implemented. It's really just a display thing for now.
if you click on one of those wires, you can have some very special purpose types.
Whoa! Cool, but this is okay, cool. And how do we unright click? Okay, that's great. Okay, bye. Work in progress. See, this is why I started this with, here are all the hard problems, because it doesn't look like much, but there's a lot of stuff. I don't know, maybe I shouldn't complain so much about my own software. Anyways, so okay, well, yeah, it's 12:30. James was like, you don't have to do the whole, like, I was stressing out. I was like, I thought this was gonna be a 5-minute demo. Do I have a half hour? How am I gonna, no, okay, I have 2 more slides, so it's gonna work out, but I thought I was gonna be much faster than this. Anyways, nested wiring diagrams via free monad. So we started out with like really hard math with left-con extensions. Now we're gonna do some more really hard math, multivariate polynomial functors. So consider the category of fillings, flung. The interpretation of an object of flung is a functor that sends the pair nm to a set of things that one might put in a box with n input ports and m output ports. Think of this as like a collection of fillings. Then directed wiring diagrams are an endofunctor on fillings. Specifically, the idea is that when you apply DWD to F and then apply that to NM, you get the set of wiring diagrams where each of the boxes has a filling given by F. So this complicated expression is you have a set of wires, a set of boxes, finite sets, or here I'm just saying that these are natural numbers. Then you have, each box has a number of inputs and a number of outputs. This is just like the set from like 1 to B. And then each wire, its source is either an input port or the output port of a box. Its target is either an output port or the input port of a box. And then I have the product over boxes of a filling of the right type, a filling of type of number of input ports and number of output ports. And so this is a multivariate polynomial functor, i.e. an endobicomodular on the discrete comodular and n squared. So David's feedback will like that, but maybe not anyone else. So this is like a little bit nicer than just an endofunctor. I'm not sure yet how to leverage the fact that it's a little bit nicer than just an endofunctor. One thing though is that, so notice that there are only finitely many things, like for each choice of stuff here, there are only, this product is only finitely many things over a finite set B, which means that we can take the free monad on DWD, because DWD is finitary. And taking the free monad on DWD gives you nested wiring diagrams, because it's like each box either contains a primitive or a wiring or another nested wiring diagram. Kind of how like in syntax trees, if you have like plus 1 times 3, 2, this is like nested. Each argument here is either an integer or another term. So how do we generalize this? What's the right notion of schema for something like this? They could generalize to like undirected wiring diagrams or other nested structures. So tell me, please. I will implement it in Scala. And yeah, this is future work, but I'm out of time. So you can look at this and then send me PRs about it. Great, thanks.
Thanks very much. So Thanks very much, Owen. So we had a couple of questions during the presentation, during the demo. Any other quick question?
Is this open source?
Yes.
Okay, while that's loading up, just to say we're going to try and have a group photo after this talk. We're going to join the other parallel session, and we're going to go outside the front of the building and have a photo.
Yeah. Sorry. And we have good API docs, not good general docs, but good API docs. I put doc strings on every single method and class. So yeah. Anyways.
Thank you very much. Any more questions, just ask on Zulip and or I guess over lunch. Yeah.
Yeah.
Can you ask, because we need to go out for the photo.
It runs low. I think we're
But it's shifting more work. Oh, okay, good. They are very